I'm going to talk to you about warranties for faster, strong consistency. This is joint work with Tom Magrino, Owen Arden, Mike George, and Andrew Myers at Cornell University. So back in the good old days, applications were backed by databases. These offered strong consistency with ACID guarantees. These were simple to program, but the problem is that they don't scale very well. So over the past decade, many systems have turned to weak or eventual consistency. While these offer better scalability, the problem is that they're difficult to program. Often consistency failures at the bottom of the software stack can percolate up and affect higher software layers in ways that are unpredictable. Warranties are a new mechanism that help bridge the gap by giving strong consistency with better performance. So what do I mean by strong consistency? Warranties offer strict serializability with external consistency. This means that transactions are atomic and isolated, and their apparent commit times agree with wall clock time. This is an intuitive programming model with no surprises for the programmer. So what is a warranty? A warranty is a time-limited assertion about the state of the system. One interesting special case is state warranties, which are about the state of an object. For example, we might have a warranty that says that Bob's account balance is 42 for the next 2 seconds. More generally, computation warranties are about the result of a computation. For example, we might have a warranty that says there are at least 6 aisle seats available on a flight for the next 5 seconds. The duration of these warranties can be set automatically and adaptively. And for the duration of each warranty, that warranty is defended to ensure that the assertion remains true. Throughout this work, we assumed loosely synchronized clocks, such as what you might get with NTP. Warranties allow commits to avoid communication while guaranteeing strict serializability and external consistency. Warranties are used in the context of optimistic concurrency control. This is usually the most scalable way to get distributed transactions that are strongly consistent. For those who missed the farm talk this morning, let me remind you of how distributed OCC works. There are 2 kinds of nodes. At the bottom of the slide are storage nodes, which store persistent data. At the top of the slide are clients, which compute optimistically on cached data. When there is a cache miss, clients read from stores. And the benefit of having a cache is that we get to avoid communication until commit time. When the commits are handled by a 2-phase commit protocol, the first phase is a prepare phase. So on this slide, we have an example of a transaction that has read a blue object, so it does a read prepare against the blue store. It's also written a red object, so it does a write prepare against the red store. If both stores agree that the commit can happen, then the commit happens in a second phase. The downside of this is that if a store holds a popular object, it quickly becomes a bottleneck. Popular objects are bottlenecks for pessimistic locking as well. With most workloads, popular objects are usually read more often than they're written, which means that the client's copy of the object is likely to be up to date. So why not guarantee the freshness of this client's cache? This is exactly what warranties do. When a client receives an object, it comes with a warranty, and this guarantees the freshness of the client's copy of that object. Because of this, warranties can eliminate read prepares. If a client has an unexpired warranty, then it doesn't have to contact the store to prepare its read. With the right data layout, this can result in the client only needing to communicate with one store, in which case the client can commit in a single phase and eliminate a whole round trip. What's really cool about this is that we can even do a 0-phase commit. So for read-only transactions that are entirely under warranty, the client can commit without any communication at all. Expired warranties can be used optimistically. When a transaction commits, the store will revalidate and extend the warranty, and the store then sends the extended warranty as part of the commit protocol. It's worth noting that state warranties generalize optimistic concurrency control. In particular, if we only ever issue zero duration warranties, then what we have is exactly OCC. You may be noticing a similarity with read leases. Leases were introduced by Gray and Cheriton in 1989. They give time-limited rights to resources. For example, with DHCP, we need to have a lease in order to use a given IP address. In an object system, we might need a read or write lease in order to read or write a given object. Clients can relinquish their leases when they are no longer needed, and this allows outsourcing of consistency to the clients. Warranties offer a shift in perspective. Instead of rights, warranties are about time-limited assertions about what's true in the system. There is some overlap here in that state warranties are similar to read leases, but state warranties naturally generalize to computation warranties. So what is a computation warranty? It's a warranty on the result of a computation. One lightweight way to present computation warranties in the language is with memoized methods. For example, we might extend Java with a memoized keyword that says that the system can issue warranties on the result of the method. So on this slide, we have an example of a memoized method declaration for a method called seats available that determines whether a certain number of seats of a given type are available on a given flight. The client code for this method is just ordinary Java code. This example displays all flights that have at least 3 aisle seats available. So let's see what happens at runtime when we call seats available. When the application calls seats available, the client checks for an existing warranty. If it finds one, then it just uses it. On the other hand, if no warranty exists, the client computes the result and creates a warranty proposal. On commit, the client sends the proposal to the store and gives it a duration. The store gives it a duration. One thing that makes computation warranties different from state warranties is that they can depend on other warranties. Memoized functions depend on the state warranties for the objects that they use. Additionally, functions can call each other, so we also have dependencies between computation warranties as well. In general, computation warranties are part of a warranty dependency tree with state warranties at its sleeves. For example, if a function f calls a function g, then this produces a dependency tree like the one shown on the right. As a more detailed example, suppose we want to know who are the most popular users on Twitter. This is a computation whose result is unlikely to change often, even though the underlying followers of the users might change frequently. For good performance, we might implement this with a divide and conquer algorithm, and this gives a warranty dependency tree like the one shown on the right. This is a good thing because if we have warranties for part of the tree, then we only need to compute for the rest of the tree. And with a warranty at the top of the tree, we get to reuse this entire computation at very low cost. This is like what memcached offers, but here we get strong consistency. So you might be wondering, why don't we just memoize all of the methods in the program? Well, the problem is that not all methods are memoizable. In particular, the behavior of a method should be identical regardless of whether a warranty is used. Not all computations have this property, so memoized computations must be deterministic, and they must have no observable side effects, which means that they cannot modify pre-existing objects. So why not memoize all the other methods? Well, the thing is that warranties aren't free. In addition to creation and bookkeeping cost, warranties need to be defended against rights that invalidate them. To defend state warranties, we delay writes until the warranties on the modified objects expire. So when a client wants to commit an update, the client sends the update to the store, and if the store notices a conflicting warranty, then the write is delayed, and the client is notified of that delayed write, or the delayed commit. When the warranty expires, then the commit goes through. Okay, so this covers defending state warranties. What about computation warranties? Computation warranties are defended similarly. When the client commits, the store puts the update aside. The store then uses the update to recompute the method. And if the result is different, then the write is delayed, just like with state warranties. On the other hand, if the result doesn't change, then we allow the commit to happen immediately. Warranties can delay writes, so the key to performance in this is to set warranty durations correctly. We want to make sure that the warranty is long enough to be useful, but short enough to keep writes from blocking. We have an automatic, adaptive, and online mechanism for doing this. And this mechanism is based on an analytic model driven by runtime measurements. This mechanism will issue long warranties for frequently used and seldom changed items, and short warranties, or none at all, for the other items. With strong consistency, a trade-off between readers and writers is unavoidable. Warranties improve read performance, but delay writes, and this is a good trade-off to make for typical read-heavy workloads. Warranties occupy a middle ground between optimistic concurrency control, in which writers abort readers, and pessimistic locking, in which writers wait for read locks. So we've implemented warranties as an extension to Fabric. Fabric is a secure distributed object system with a high-level programming model that presents persistent data to the programmer as ordinary language-level objects. We've implemented support for both state and computation warranties, and we have extended the Fabric language with Memoized methods. The base Fabric system consisted of 44,000 lines of code, and the warranties extension added or modified 7,000 lines of code. To evaluate state warranties, we used a multi-user 007 benchmark. This benchmark models applications that are built on object-oriented databases. The transactions in this benchmark are relatively heavyweight, involving 500 objects. We changed the benchmark to model popularity of reads using a power law distribution. This increases read-write contention in the system and makes the system harder to scale. We ran our experiments on a eucalyptus cluster in which the stores consist of 2 cores and 8 gigs of memory, and the clients are twice that size. This graph shows the scalability of Fabric and warranties as we increase the number of stores. On the vertical axis, we have maximum throughput expressed in transactions per second, and the x-axis shows the number of stores. The workload we ran consisted of 2% writes, and we ran with 36 clients. Fabric, shown in red, shows little improvement with more stores. And this is because the system was bottlenecked at stores that contained the popular objects. Warranties, in green, gets about 400 transactions per second per additional store. Because warranties is a mechanism that is tuned for read-heavy workloads, we increase the fraction of writes in our workload to see what happens. On this graph, we have maximum throughput, again, in transactions per second on the y-axis, and read percentage on the x-axis. We ran with 3 stores and 24 clients. And so up to 5% writes, warranties gets at least 2x speed up over Fabric. And at 10% writes, the cost of issuing and defending warranties is too high to give improvement. Across all of these runs, the median write delay was 0 milliseconds. And in fact, 70 to 80% of all writes were able to commit immediately. To evaluate computation warranties, we ran the Twitter example as a benchmark. This example involved 100 users, and the workload involved 98% reads that continually recompute the top 5 users. The workload involved 2% writes that follow or unfollow a random user. This workload models having the top 5 users displayed on the Twitter homepage. State warranties improves throughput over Fabric but increases latency. For computation warranties, we get increased throughput by over a magnitude or by over an order of magnitude, while greatly reducing latency and write delay. Computation warranties get this speed up by giving application-specific consistency. We also evaluated with a real web application. The Cornell CS Course Management System is a web application for managing assignments and grading in the Cornell CS department. To establish baseline performance, to establish a baseline for performance comparisons, we ported CMS to Hibernate, which is a popular ORM library for building web applications. We ran Hibernate in optimistic locking mode, which is considered the emerging best practice. We also ported CMS to Fabric. The workload we ran is based on a 3-week trace from the production CMS system. This graph shows the maximum throughput in transactions per second for Hibernate, Fabric, and warranties for a single store. Fabric provides performance that is at least competitive with Hibernate. And adding warranties improves performance further with this real-world workload. When we go to 3 stores, this graph shows that warranty scales better than Fabric. There is much related work. The most closely related work is listed here. Warranties is the first to provide strong consistency by defending client caches. So I've presented to you warranties. Warranties help bridge the gap between consistency and scalability. By defending client caches from invalidation, we get to avoid communication during commit while enforcing strict serializability and external consistency. Thank you.
Aaron, University of Wisconsin. So you mentioned that you're using this analytical model to set these warranties, and you said they could be short or long. How long of warranties are we potentially talking about setting here? On the order of seconds, tens of seconds?
So seconds, in our experiments, we let them go up to 10 seconds long, but it really depends on the performance characteristics that you want to provide, how long to set the maximum warranty length.
Okay, and then my follow-up question to that is, if you determine that you've set a warranty that's too long and you're ending up blocking a lot of rights, is there a way to safely revoke the warranties?
No, there is not.
Eddie Kohler, Harvard. This is really cool work. I have first question. So if you set all of the warranties to 0, do you perform the same as OCC or do you perform worse? And if so, by how much?
So we didn't measure this. I would expect that we would perform slightly worse simply because of the overhead of the warranties mechanism.
Right, but you think the overhead is pretty small? It seems like it could be.
I would expect so, yes.
Okay. And the other question was, did you find that there were certain kinds of computation warranties that were more useful than others?
So this is a good question. So yes, in that not all methods are worth having the overhead of doing computation warranties on. So typically you want to have a computation that is over a large set of data, like the Twitter example.
Thanks.
Alec Wallman from Microsoft. I was wondering, is it the case that you need to understand a lot about the sort of detailed workload characteristics in order to figure out what are the appropriate computational warranties to set for your system, or is that not really the case? Because it looked to me like in some of the examples, it might well be the case.
Yes, I think that's a fair characterization. Yeah.
And so if the workload characteristics change a lot over time, what do you imagine then would be sort of the programmer effort in figuring out how to tune your system to continue to perform well?
So, sorry, can you ask that again?
Yeah, so if you need to have a pretty detailed understanding of the workload characteristics in
Yep.
order to figure out how to write these computational warranties, and then if the workload characteristics of your system change over time, how do you imagine that the developers of the system
Right.
should be?
So this is not something that we've thought deeply about. Currently, as things stand, you would need to reevaluate which methods you've memoized and reevaluate whether it's worth keeping those memoizations or worth memoizing new methods. Yeah.
Thanks.
So I have a quick question. So in terms of performance, it seems like the higher throughput comes at a latency cost. In terms of performance, I was sorry. I was just asking that in terms of speaking more about performance, it seems like you get higher throughput, but it's coming at a latency cost. Can you comment on what the implications of that are? And let's let the other speaker set up.
So the latency cost is only for write transactions. So if you have a workload that, if you have a workload that is mostly read-only, then perhaps this is acceptable. I mean, it really depends on like how much of a delay you're willing to accept for your write transactions. But I mean, for read transactions, you actually get a large improvement in latency, right? So.
All right, let's thank Jed once again.